All right, so we're going to start off before we jump into the 3D shape of molecules by covering just a little bit, about 5 slides about sulfur. So this is the stuff we just didn't quite get to when we were talking about alcohols. So anytime you see sulfur, it is classified as typically as a thiol, and thiol just technically refers to SH or sulfur hydryl group. You can see sulfur hydryl here, bound to a carbon. That's the generalized formula that we will see. So nothing crazy, but that's our sulfur groups. And when sulfur is attached, you typically see a bent shape. Now, why is that? Well, if you look at the periodic table of the elements, you'll notice that sulfur sits directly below oxygen, which means they have relatively similar electronegativities, relatively similar sizes and behaviors. So thus, typically when you see sulfur, it acts a little bit like oxygen in terms of its behavior. Now, sulfur is obviously bigger than oxygen, right? It's nearly double the size of oxygen. No, sorry, it's nearly 1.5 times the size of oxygen, space-wise. So it does behave slightly differently, but as a general rule, sulfur and oxygen behave pretty similarly. Now, thiols don't contain OH bonds, so they're actually incapable of intermolecular hydrogen bonding. So even though you see this SH, you don't treat it like an OH bond. So that means sulfur is just incapable of forming hydrogen bonds. So remember when we saw alcohols and they would form hydrogen bonds because they had that OH bond? Sulfur just simply doesn't do that, just doesn't. But thiols ultimately have a lower boiling and melting point to similarly sized alcohol. So if we have ethanol, the fun time alcohol, and then ethane thiol, CH3, CH2, SH, you'll notice that the boiling point is about half. Why is that? This guy does not do hydrogen bonding. This guy does hydrogen bonding. So remember, one of the things that gives water its sort of unusual characteristics is all of its hydrogen bonding. And sulfur groups just simply don't do that. Now, to name a thiol, it's actually relatively straightforward. We're kind of just building on this IUPAC system we've been using, but we name the parent hydrocarbon chain as an alkane. Then we add the suffix thiol, and we number the chain to give the SH group or the thiol group the lowest number. So the most simple thiol we can see is CH3SH. Remember, CH3 is methyl, so we have methane thiol. Methane thiol. Remember, CH4 would be methane, methane thiol. If we have propane, CH3, 1 propane thiol. So we have to, in this case, we have to designate where that SH group is with the 1 dash proponent. Now, in the methane diol, there's only one way to link it up, right? Because there's only 1 carbon in a methane. So just as to know. But again, it's very straightforward, right? It's like naming an alcohol. You just tack on something, and that thing you tack on is the thiol, trying to give the thiol the lowest possible number. But remember, at the end of the day, even if you encountered a thiol and an alcohol on the same molecule, you're trying to give the lowest numbers possible. So that's always kind of an important thing, right? If you can go 3, 4, it's better than going 4, 5, right? Based on the IUPAC system. So thiols are important for biology. Now, there's a whole groups of microorganisms on this planet that specialize in the use of inorganic and organic sulfur in their metabolisms. That doesn't mean too much to you guys, because you don't care about microbes. I do, but you don't. But thiols are actually important for amino acids. And so we'll talk about amino acids later in the semester, but thiols characteristically have a scent of foul odor. So typically thinking like skunk. The big one is rotting eggs. So when you guys smell rotting eggs, it's usually a foul odor that's associated with thiols. But we also see onions have thiols in them. The smell of skunks. There was a skunk dead on my road this morning, and it stunk to high heaven, all because of thiols. Now, interestingly though, thiols can be oxidized to what we call disulfides. So we take a thiol, it doesn't matter what it is, and we oxidize it. So remember, O inside of brackets refers to the oxidation. So we're stripping electrons away from the sulfur. We can actually form what we call a disulfide bond. And the disulfide bond is simply an SS bond. Now, this might not seem super important, but I just want to go over one last thing before I talk about why it's important. Now, disulfides like this can be broken through reduction. So we see H, we're adding H back in brackets. That's a reduction reaction, forming a new thiol bond. Now, I said disulfides are important, and they are. Now, one of your amino acids, cysteine, contains sulfur. Now, you guys may remember from introbio, or maybe if you've never taken introbio, this will be brand new news for you, but amino acids are the components of proteins, right? They're the building blocks of our proteins, and proteins do everything inside you. They're basically the machinery that makes you you. Now, cysteine will form, because it has sulfur in it, it will form these disulfide bonds. And what this does, it actually helps proteins that contain large amounts of cysteine amino acids to actually become a little bit more stable. It's a very strong bond, a sulfur bond, a disulfide bond. So again, it's not too common, but you do see it inside of your amino acids in your proteins, helping proteins get that nice little fold that they depend on. So kind of an important part of molecular biology. And I just wanted to mention it because these sulfurs are kind of abstract outside of being stinky things. But again, this disulfide bridge, an SS bond, helps hold some of your proteins together. So that's going to be our thiols. As I said, it was just going to be a few slides. Let's move on to the next part. And this is actually my least favorite part of all chemistry. And I'll explain why in a minute. But our next part of our lecture is going to cover the 3D shape of molecules. So just as a review, isomers are different compounds that have the same exact molecular formula. And constitutional isomers differ in the ways that our atoms are connected to one another. So we can look at an example here. We have constitutional isomers. They have the same functional group. So they have a methyl group here, but it's simply tacked on to a different carbon. So it's at carbon 2 here and carbon 3 here. So these are isomers, but they are technically constitutional isomers because they simply differ in the way that they're attached. So we talked about this before. This is nothing new, but just a refresher. Now, constitutional isomers can also be slightly more complex. So we can look at this chemical formula, C6H6O, and you'll notice I have ethanol and dimethyl ether, sorry. Same chemical formula, but different functional group completely. This one we have an ether. This one we have an alcohol group. So they are technically isomers, but let me ask you this question. Do you think these have the same properties? Does an ether have the same properties as an alcohol? Ilsa's shaking her head no, and she is absolutely right. Ethers behave very differently than alcohols, right? Alcohols have hydrogen bonding capacity, right? Ethers do not. So they are constitutional isomers, same exact chemical formula, different arrangement of atoms, but the differential arrangement of atoms here is such that we get a completely different functional group. Now, stereoisomers, they differ in only the 3-dimensional shape. Now, the one we talked about the most is cis and trans, but remember, for something to be a stereoisomer, it has to have the same exact functional group. So in this case, these are not stereoisomers because we have an alcohol group and an ether group here. Constitutional isomers, but not stereoisomers. So the one we talked about was cis and trans. So remember, cis is where everything is on the same side of a double bond, and trans is when things are diagonal across a double bond. These are stereoisomers. The functional groups are identical, right? In this case, the functional group is just an alkene, right? The double bond. Just a review. Now, this is the part of this lecture that I don't like. And this is topic that we're going to talk about is what we call handedness, or better known as enantiomers. And I don't like this part because it just makes chemistry way too abstract to me, but let's get into it. Now, when you look at your left and your right hand, and you guys can do that, you can just look at your left and right hand. Well, they're mirror images of one another. And well, what do I mean by that? Well, if I put them up next to each other like this, they're identical, right? I mean, there's slight variation, obviously, but when I look at my hands, I can fold them over and my fingers line up perfectly, right? Index finger with index finger, and so on and so forth. So left hands and right hands are mirror images of one another. You can also think, your laptop, right? Your screen of your laptop. You cut it down the middle, it's the same, right? Just a screen on both sides. Handedness. Now, this is where things get kind of weird. Now, left and right hands are not identical. And That's not just because they're different in terms of stuff. They're actually just not superimposable. And you can just see this yourself. If you take your left and right hand and you go like this on top of one another, well, that's not a superimposed image, right? If I took my left hand and put it on top of someone else's left hand, well, they're in the same orientation, slightly different size, obviously, but they're going to be essentially identical. So again, they're mirror images if you reflect them over, but if you put them directly on top of one another in the same orientation, they're not superimposable on top of one another. With you thus far? It's kind of a weird thing to think about. I don't think you've probably never thought about your hands this way, but that's how they are. So a molecule that is not superimposable on its mirror image is what we call chiral, C-H-I-R-A-L. So let's give you another example. Let's go to your socks. So two socks from a pair are mirror images of one another. You can flop them over, right? If I have two pairs of socks, I flip one over onto the top of one another, that's a mirror image. Conversely, if I laid one sock on top of the other sock, they are also superimposable, provided they're from the same set. So a molecule that is superimposable, like our socks, on its mirror images are what we call achiral. So chiral is your hands, achiral is your socks, and there's lots of examples of both of these, but these are sort of the most simple, average, everyday ones that you're going to see. Sock and hand for chiral and achiral. So how do we figure out if a molecule is like this, right? Because we're not talking about socks and hands because we're in an anatomy class or anything like that. We're talking about socks and hands because it's a chemical property. And it's a chemical property that actually has some really interesting real-world applications that we'll get to. But to test whether something is chiral or achiral, we simply draw the molecule in 3 dimensions. Then we draw its mirror image. And then we try to align all bonds and atoms. Now, to superimpose a molecule and its mirror image, you can perform any rotation, but you physically cannot break bonds. So let's look at water. Water is achiral, so I'm going to give you the answer right now. But we can draw water in its 3D image. Now, water, remember, it is all on one plane, right? So we can draw water like Mickey Mouse, but it does have that 109.5 degree bond angle that we know and love for water. Now, we draw water, and then we draw its mirror. So if this is our original molecule, we draw its mirror image. Again, all I would do here is just flip this water like this, giving me the mirror image of water. Then, once I have that mirror image, I take one and simply stick it on top of the other. Now, if they align perfectly, these molecules are achiral. If they do not align perfectly, I can rotate. I can't break bonds or reform bonds, but I can rotate as I need to try to get them to align. And so in this case, water is achiral because it has a mirror image of itself. And you'll be able to get this for all molecules that you draw. There is always a mirror image. And the question is, do these mirror images line up perfectly in 3D space? And in this case, water, it does. So let's look at a slightly more complex example, CH2BrCl. So it's a halogen attached to some alkane, right? So we can draw CH2BrCl, and it looks like this in 3D space, right? We have one carbon that's bound to 4 things, so it takes this standard shape that we saw with methane, right? Similar bond angles, so on and so forth. Now, our mirror images is, we just flip it over this axis. So now we have our bromine here, our chlorine here, carbon here, hydrogen's here, 3D image. Now, the question is it chiral or not? Well, what I'm trying to do is superimpose this on this. And remember, you can rotate as you please to try to align the molecules. And in this case, you can actually rotate to align these molecules perfectly, giving us an achiral molecule. So let's step up the difficulty slightly. CH2BrClF. So carbon bound to 3 halogens. Fun stuff. Now, we take the mirror image of this molecule, again, flipping it just like over this axis. So again, it's like almost like flipping a piece of paper, right? That's like when I remember when I was doing this long time ago, that was like what the person told us, like, oh, think about it like you're flipping a paper, right? If this is on one sheet of paper, right, you might see the molecule through the paper. And then if you turn that paper, it's going to be in this other orientation here. Now, if we try to superimpose these one on one another, well, it doesn't quite work, right? Yellow aligns with yellow here, but green and red don't align. If you're colorblind, I'm sorry, I didn't think that these colors would be so bad. So if you're colorblind, I really apologize. Red, green, colorblind, of course. Right? So they don't quite match up. If I flip this over, no, it doesn't quite give me the same 3D structure as I would like. If I try to align these together, again, it doesn't quite give me what I'm looking for. So these would be chiral. Again, I know, weird, but you'll get time to practice this, and we'll go over it more on Wednesday. Don't worry. So what's going on here? Why? I mean, these are achiral. I'm sorry, these are chiral, I should say, because they don't align. But we can actually look at these mirror images and give a new term. Now, the two mirror images of CHBr, CLF are what we call enantiomers. And enantiomers are mirror images that simply are incapable of superimposing. And you can see that here. They're mirror images, but they're not capable of superimposing on one another. Now, a molecule that is not superimposable on its mirror images, as we mentioned, is called a chiral molecule. Now, a carbon that has 4 different atoms attached to a center carbon, like we saw with CHBr-CLF, is what we call a chirality center. Now, molecules can contain 0, 1, or many chirality centers. So in the case of here, we had 1 chirality center. So there's only 1 carbon with things attached to it. But you can have more chirality centers as molecules get more and more complex. So the question is, how do we identify a chirality center? Well, the reality is we look at each tetrahedral carbon atom in a molecule. So carbon, remember, it's always going to be bound to 4 things. It's always going to want to take that standard tetrahedral shape, right? It's always going to want to do that. Now, if we look at the 4 groups, not the 4 atoms that are bonded to it. So in this case, we have a carbon that's bound to 4 different halogens. And we want to know if they're different groups. So in the case of a couple slides ago, just go back, we had CH2. Well, those are not different groups, they're identical, right? So in this case, we only have 3 distinct things bonded to our main carbon. So again, we're looking at what 4 groups, not 4 atoms. Now we kind of interchange atoms and groups together oftentimes, right? Because chlorine and bromine are technically groups, but they're also atoms, right? So, and we also need to consider all atoms in a group as what we call a whole unit. And so we can look at this carbon, the center carbon. It's got 4 things coming off it, as all good carbons do. Now it is bonded to 4 distinct groups: H, Br, an ethyl group, as well as a propyl group. So we have 2 different alkyl groups here, ethyl and propyl, in addition to a hydrogen and a bromine. So in this case, our chirality center is going to be here in the center carbon. That's kind of a theme. It's always going to be in the center carbon, kind of the rule. So when we look at 3-bromohexane, we can identify its chirality center as the C in the center here. Okay. So a carbon atom that is bound to 2 or more like groups is never a chiral center. So 2 or more like groups is the key here. Now, what do I mean by that? Well, CH2 and CH3 groups have more than 1 hydrogen atom bound to the same carbon. So these carbons are never chirality centers. A C that is a part of multiple bonds does not have 4 groups around it, so a double bond or a triple bond. And so it's also never a chirality center. let's think about chirality centers in these two hypothetical molecules, tartaric acid and ephedrine. So this is a decongestant. If you guys might have taken ephedrine. It's like it's gonna be similar to like Benadryl. Like it's an antihistamine sort of thing. Now we can look at tartaric acid and ephedrine. Now we have carbon, 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 and they're bound to, again, very similar aspects. So this is bound to a carboxyl group here, alcohol and hydrogens. Now in this case, we have two chirality centers in both because they're bound to 4 distinct things. 1, 2, 3, 4, 1, 2, 3, 4, and then so on and so forth. So in this case, our red is our chirality centers. So what does that bring us problem-wise? Well, we're going to go over more of these Wednesday, but we'll do an example here. So we're going to draw the 2 enantiomers of D-butanol in 3D around the chirality center. So in this case, we've already given you the chirality center of 2-butanol. Why is it 2-butanol? Well, we got 4 carbons, and the oxygen is coming off the second carbon from the left. So 2-butanol. So we first draw one enantiomer by arbitrarily placing the 4 different groups at opposite corners of a tetrahedron. Now remember, we have a tetrahedron, so there is that 3D space. We have the dashed line and the sort of the solid line. Does anybody remember what those indicate? Well, one's coming at you, and one's coming away from you. Yeah. Sure. Which one's behind and which one's coming towards you? Exacto. So dark lines coming at you, dashed lines going away from you. So like we're thinking about 3D space. The dark ones are coming straight out of the paper. The dashed ones are going directly through the paper to the other side. Remember, we draw these in 2D, but there is 3D shapes to this, right? Chemistry is 3D, it's not 2D. It'd be easier if it was 2D, right? We wouldn't even have this lecture, but chemistry is 3D. So it's carbon, it's tetrahedron, so it has that distinctive tetrahedron shape, and we have to draw that. If you need a refresher on what that looks like, this is what methane looks like. Remember, CH4, methane always takes that tetrahedron shape. Then we have to add the groups. Now, if we go back to the slide, we have CH3, OH, an ethyl group, and then a hydrogen molecule. And we simply have to tack these on in any arbitrary order, but we want to put the 4 different groups at opposite corners of the tetrahedron as best we can. So we went from this to this. Step 2, we want to draw, you don't have to do this when you're drawing it, but theoretically, you'd want to draw a mirror plane, and then you need to arrange the the substituents in the mirror image so that they are the reflection of the first molecule. And again, it's about taking this and flipping it like this. So what ends up being here, it's flipped over like this. What ends up being here, it gets over here, and this is at the top, just stays there. Now, you could also imagine, well, what if I put the ethyl group here and the methyl group here and the hydroxyl group here and the hydrogen here? It'd be the same result, right? Right. You're still just trying to draw a mirror image. So it doesn't really matter where you put them at the end of the day, as long as you put them. That's all you have to do. So we have this structure here. Now the question is, once we do a mirror image, are they superimposable? Did I put a figure here? No, I didn't. Again, all that would require is just me moving this over. And do they match up in 3D space? And they're just not, right? If you move this on top of this, well, the H and the OH are here, the CH2, CH3 is here, the methyl group is there, but they don't quite match up. Match up in 3D space, right? So in this case, they're simply not superimposable. If I just drag this over, again, it's in different 3D space. Thus, these are not chiral, They're achiral, thus they are enantiomers. It's a fun word to say. So how do we identify chirality centers in cyclic compounds? Ring structures, fun stuff. So we have methyl cyclopentane, pentane because it's 5 carbons, and then we have a methyl group coming off carbon number 1, thus it's simply methyl cyclopentane. So where do we identify the chirality center? Well, we need 4 things coming off, right? Now, technically, we could think of, well, a chirality center could be here, 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 or here. But when we think about here, right, remember there's 2 hydrogens coming off here, and there's a carbon here and a carbon here. So they're 2 identical groups. So it's not 4 distinct things, it's 2 identical groups. So these don't quite work as chirality centers. Neither does this, neither does this. However, when we have our substance coming off here at C1, it's got a hydrogen and a methyl group, but again, a chirality center. Oh, I thought where's my slide? I'm sorry, I'm missing a slide here. I guess I accidentally deleted it. I'm sorry. I'll have to post a new one to Blackboard then. That's weird. Anyways. That's weird because there should be, anyways, there should be another slide, but let's go on to this next example and I'll post the actual slides. Now, is C3 a chirality center? Well, we have 3-methyl cyclohexene, ene, we have the double bond, 3, because this would be carbon 1, 2, 3. There's a methyl group coming off carbon 3. Now, the question is, where's the chirality center here? Well, C3 is the chirality center, and if this isn't the chirality center, why are they different? Well, the key here is, well, what's coming off? Right? If this is a chirality center, which it tells you yes, so I'm kind of giving away the answer, but what's coming off this? Well, we have a carbon here, a double bound carbon here, a hydrogen, and a carbon here, 4 different groups, thus this has to be a chirality center. In the previous slide, all these carbons all have the exact same stuff coming off them. And even this one has 1, 2, only 3 distinct things coming off of it. Thus, it's not a chirality center, right? You need 4 distinct groups coming off for it to be a true chirality center. So, hope you guys are having fun. Now, many biologically active compounds contain 1 or more chirality centers. So for instance, I have 2 slides on this. So thalidomide, which was actually, it's used for a couple different things, but in the 1960s and late 50s, it was actually used as an anti-nausea drug, and it was given to pregnant women in the early 60s, and this had a chirality center. Interestingly enough, because it had a chirality center, it means it had some 3D aspects to it, and it actually had 2 enantiomers. So, interestingly enough, the thalidomide that was being sold to pregnant women as an anti-nausea drug, it was a really, really effective anti-nausea drug. I'll just make mention of that. It was actually sold as a mixture of the 2 enantiomers, left-handed and right-handed, both of which actually didn't have the same biological effect. Now, one of them was a fantastic anti-nausea medication. The other one was actually causing catastrophic birth defects in women. Why? They just differed in their arrangement in 3D space, which is kind of crazy, right? Same compound, same chemical formula, slightly different arrangement in 3D space. One cures nausea fantastically. The other one was causing catastrophic birth defects. Pretty wild. There's a really cool story behind this. We're not going to talk about it, but definitely look up thalidomide if you have like 5 minutes to go down a rabbit hole. It's actually a really fascinating story about the interplay between like pharmaceutical companies and the government and citizens being, awesome citizens and fighting for things. It's actually a pretty cool story. But we can look at this. We have our chirality center. So this is our anti-nausea drug. It looks like this. It's mirror image. Again, it has a chirality center here. Well, why does it have a chirality center? 1, 2, 3, and 4 distinct things come off of this molecule. And again, we're counting this double bond bound to this carbon as a distinct thing from just say this, which is just a carbon bound to 2 hydrogens. When you flip it over, it becomes pterygotin, or pterygen, pterygen. And if I try to move these on top of one another, I'm sure you guys can see that this does not match over here. Thus, they're enantiomers. Good drug. Make your babies come out with 10 extra fingers. Bad drug. Not that extreme, but you're talking like misformed skulls and stuff like that. So chirality plays an important role in cyclic compounds as well as medicine. Now, like thalidomide, I want to say thimerosal, but that's the wrong molecule. Now, many drugs that we use are chiral, and they often have to interact with the chiral receptor to be effective. Now, this is kind of a cool aspect, and it takes us into the world of neurobiology, which I think you guys might find a little bit fascinating. Now, one enantiomer of a drug may actually be effective in treating a disease, while its mirror image might actually be ineffective, and as we saw with thimerosal, was completely damaging, right? Just wasn't doing what it was supposed to. Now, it's kind of an interesting thing. If the other enantiomer is not biologically active and the other one is, it's what we call a racemic mixture, which is a kind of a fun word to say. And a racemic mixture is typically an equal mixture of the two enantiomers. So let's think about what this looks like. So we have phenylalanine, and then we have phenylalanine as well. Does anybody recognize phenylalanine? You should. It's amino acid, right? So your proteins, right? It's amino acid, phenylalanine, it's good stuff, right? Now, biologically speaking, if we're thinking about phenylalanine A versus phenylalanine B, again, you can see they're mirror images of one another. They're enantiomers, right? Because they're not chiral. They would be achiral, right? This is not superimposable on this, right? And if you think about the receptor for phenylalanine on one of your cells, for instance, well, if phenylalanine typically looks like this, well, there would be a receptor that might have a big opening and a small opening and then a slightly small opening for phenylalanine to basically slot itself in, thus be recognized by a cellular protein. This is how receptors on your cells work. It's like it's a game of like, does it fit or not? Now, conversely, you can imagine if they have the same exact cellular protein receptor, well, this enantiomer simply doesn't fit, right? This left-hand inversion, which again is in this orientation, not this orientation, it just simply doesn't fit, right? You guys played that game when you were kids, when you had to put the blocks in the holes, and there were circular blocks and square blocks and triangular blocks. You guys know that you can't fit a square block into a round peg hole, right? Same idea here. And so again, it does play an important role in biology, right? Molecular biology of your cells, for instance. Now, ibuprofen. So if you guys have ever taken Advil, its molecular name is ibuprofen. Now, ibuprofen is an NSAID, so non-steroid anti-inflammatory drug, and it's kind of interesting. It has an enantiomer pair. Now, its enantiomer pair is inactive, so ibuprofen, and then it's inactive enantiomer here, and it's actually sold as a racemic mixture. So when you buy Advil, and then maybe you buy ibuprofen from CVS or Walgreens, you're actually not getting pure ibuprofen. You're actually getting a racemic mix. Regular, awesome ibuprofen that gets rid of your body aches and your headaches, and then the not so fun inactive enantiomer. And why is that? Well, again, it's this idea. Ibuprofen targets your cells, and if it can't fit into the receptors on your cells because it's the enantiomer, it's simply not going to be effective. Same exact chemical formula, same exact structure, different 3D orientation. I know this is why I don't like this stuff. It's just really abstract, but it is what it is. Now, naproxen, or some people call it naproxen, you guys might have taken a leave before in your life. It's a long-term, 12 to 15-hour pain reliever. Actually, it's kind of interesting. Now, when you buy a leave, it's not a racemic mixture. Why isn't it a racemic mixture? Well, naproxen normally looks like this. Its enantiomer, actually kind of interesting, is toxic. So if you take a racemic mixture of Aleve, or maybe you go to CVS and you buy, naproxen as like the generic brand or something like that, well, it's an enantiomer, which you don't typically find in like over-the-counter medicines, is actually toxic to your liver. It actually starts to build up into your liver and helps shut down your liver function. So kind of interesting, when they are manufacturing this, they actually have to take great care in purifying out this enantiomer as they're synthesizing naproxen. So no effect in Advil, pretty dangerous effect in Aleve. Now L-Dopa, which is a precursor to dopamine. So I'm sure you guys know sort of dopamine. It's one of the signaling molecules in your brain. And L-Dopa is actually, as a molecule, is actually used to treat those that have Parkinson's disease. For those of you that might know, those that have Parkinson's have a severe deficit of the signaling molecule, dopamine, inside their brains. Now, dopamine can't be directly taken by a patient because it actually doesn't have the capacity to cross the blood-brain barrier, or your meninges, right? That barrier that's around your brain, right? That keeps your brain distinct from the rest of your body. Brain chemistry is weird. There's all sorts of cool stuff. Now, L-Dopa, which is the active agent in active against Parkinson's disease, it easily fits through your meninges, your brain blood barrier. But it's D-Dopa, so left-handed dopa versus right-handed dopa. Well, this one simply cannot pass through your cell membrane, thus it cannot help treat Parkinson's. And I should also mention, there's some other side effects to D-Dopa versus L-Dopa. And you can just sort of look at this if you want to see a schematic of what this looks like. You have your brain, you have your dopamine release from your neurons, and then there's dopamine receptors. And when dopamine is released by one nerve cell, it binds to the receptors on another one in a target cell, right? That's how your brain cells work, right? They just release chemicals between one another, and that makes you happy or sad, which is kind of a sad way of putting it, but it is what it is. Now, those with Parkinson's disease are characterized by the degeneration of the dopamine nerve pathways in the basal part of your brain. So right here, it's called the basal ganglia. Now, L-Dopa is given to people, not D-Dopa, but L-Dopa is given to people because it can actually help synthesize dopamine from it, thus reopening this pathway for those that suffer from Parkinson's. Not fully, of course, because if L-Dopa was super duper effective, Parkinson's wouldn't be as sad and depressing disease as it is. So, all right. So we have a rehash of a term. We've brought it up briefly, but we're going to talk more in depth about this. What we call a Fischer projection, which I think is apt because we're sitting in Fisher College, spelled differently, obviously. We're F-I-S-H, and this is F-I-S-C-H. But Fisher College, Fischer Projections, they go hand in hand. Now, a Fischer projection takes into the 3D tetrahedral shape and redraws it. So we draw a tetrahedron as such. So we have C, two black diamonds, and then two dashed diamonds. Now, these horizontal bonds themselves come forward towards you on wedges. And remember the vertical bonds, the dashes go backwards on dashes. So we draw a tetrahedron such as this, and then we abbreviate as a cross formula such as this. This is a Fischer projection formula. So it's a bit different from what we've seen thus far, but Fischer projections are really common when we're thinking about this 3D structure. Drawing like this, and then drawing a Fischer projection formula as such. So let's try to draw the two enantiomers for 2-butanol. So we have butanol here, C, CH3, CH2, CH3, OH, H. Now, when we're drawing this alcohol, right? When we think about when we've been drawing, say the skeletal structure of this molecule, remember there would be this kind of kink in it, right? And you can see that in this 3D shape, right? If we put a skeletal structure over this, it would be that kink we see in the skeletal structure. So this is one enantiomer of butanol. We flip it over, getting the second enantiomer of butanol. And we can simply simplify this, again, this indication of a 3D structure with a simple skeletal structure. where we have this is converted into this, and this is converted into this, these being interchangeable. We know that this has to equal this, and this has to equal this. There's only one way to draw it. And you'll notice that, well, if I think this is maybe a bit easier to digest as opposed to this, but that depends on you as a person. But ultimately, we're replacing the chirality center with a cross. Right? The chirality center is this carbon because there's 1, 2, 3, 4 different groups attached to it. Thus, it's a chirality center. And we're simply replacing it with the cross. So anytime you see this, it's one of our chirality centers in a Fischer projection. And again, center in the middle, it's kind of like a skeletal structure, right? You know, we know where there's a point, there has to be carbon, and we're kind of seeing that here as well. Now, there's some really interesting optical activities of enantiomers. Now, two enantiomers have physical properties, that are identical. So melting point, boiling point, solubility, et cetera, right? They're the same molecule, right? If this is going to be soluble in water because of the hydroxyl group, well, this has a hydroxyl group too, thus it is also going to be soluble in water. Okay? That's sort of what we're getting at. Same chemical formula, right? So the things that we know, like as we increase the amount of carbons, right, boiling points and melting points change. As we add alcohols or thiols, it changes the boiling points as well, right? So same physical properties, melting point, so on and so forth. But they differ actually with how they interact with plane polarized light. So if you guys have ever taken physics before, you'll know light is a crazy thing. Light's really cool. If you haven't learned about light, it's a weird thing because it's a particle and a wave at the same time. And so light does all sorts of cool things. Now, we can look at a plane polarized light by taking an average everyday light source. And this is what it looks like, right, as it projects out into 3D space, right? If we have a shining coming from a bulb, and even when you can't see it, right, it's kind of just filling all the space, right? Now, you can have it go through a polarizer. And what actually happens is it takes the light waves, which are oscillating in all planes, right? So X, Y, and Z, and it just makes them oscillate. So when I say oscillate, I just mean it's going from a wave, right? Oscillation is like a wave. And then it makes it into a plane polarized light where the waves oscillate in a single plane, in this case, up and down. With me thus far? We're going from waves going out in all directions to just waves going up and down. That's what polarization does. So if you have like polarized glasses, for instance, it's changing the light in such a similar manner, just as a note. Now, a compound that is achiral, so it has enantiomers, does not change the direction of plane polarized light and is what we call optically active. Conversely, a chiral compound rotates the plane of polarized light through what we call angle alpha and is actually optically active. So we can just look at what this looks like. Light source, ordinary light, it goes through a polarizer, thus creating plane polarized light. And then we have this sample tube where we have a chiral compound. Now, what exits this is going to be plane polarized light. And you have the person looking through an analyzer to detect it. It's super duper advanced stuff here. This is more complex in real life, but simplified, this is what it looks like. And so this is how we sort of look at optical activity in terms of these chiral molecules. And again, we have a achiral molecule. If it's achiral, the plane of light doesn't change. It just stays up and down as the person observes it. But a chiral molecule will rotate the plane of light. So in this case, we have a chiral compound, and we're going from vertical lines. So again, thinking the waves going like this, up and down, it rotates them to be in a different plane, thus the person can observe them. Does that make sense? It's kind of a weird thing. So it's kind of a weird property and cool property of chiral and achiral molecules. Now, if the rotation is clockwise, the compound is what we call dextroratory. I got that one right. And it's a plus enantiomer. If the rotation is counterclockwise, the compound is levoratory. I got that one right too, which is the minus enantiomer. And the two enantiomers wrote plane polarized light to an equal extent, but in opposite directions. So we can just actually quantify this. And just in terms of like things to remember, This extra stuff is actually just extra stuff, just like cool properties of things. What we talked about in the first part of the class is what's really important. Just as a note, this stuff is kind of abstract, but it is a cool property of these molecules. Now, the specific rotation at the standard alpha angle for a specific enantiomer of a specific compound. So we can look at S-glyceraldehyde and R-glyceraldehyde. You'll notice that they are mirror images of one another, right? Whoop. But they're not superimposable, thus they are enantiomers. Now, this alpha angle here at the central carbon is slightly different, minus 8.7 and plus 8.7, making this one laboratory and this one dextroratory. So that's just a cool property. You don't need to remember it, but I just figured I'd make mention of it because we're talking about chirality here. Now, what do we do with compounds with 2 or more chirality centers? Let's step up the difficulty. Now, a compound that has 1 chirality center, as we discussed, has 2 stereoisomers or a pair of enantiomers. Now, a compound with 2 chirality centers has 4 possible stereoisomers. Makes sense, right? We just double the amount of ways that we can flip this thing. So for instance, the amino acid threonine, so it's part of your proteins, has 2 chirality centers here in red. Why are they chirality centers? Well, carbon is bound to 1, 2, 3, 4 different things. This carbon is bound to 1, 2, 3, 4 different things. Thus, it has to be chirality centers. Now, we can actually physically look at the chirality centers here. So A, B, C, and D, in this case, are our 4 stereoisomers. And these 4 stereoisomers have 2 chirality centers. So you can notice that between A and B, we're flipping the molecule like this, right? So we're allowing the molecule to flip over, right? And that's because we have H and CH, I'm sorry, H and N on this side and H and O on this side. Now, if we flop that, we put H and H here and NH and OH here, and we flip that, we get our second pair of enantiomers. So A and B and C and D are the pairs of enantiomers. So if I presented you with this, this has to be its enantiomer, but know that there are 2 other enantiomers that we can see. Now, A and C and B and D are what we call diastereomers, and are stereomers that are simply non-mirror images of one another. Well, why is that? If I flip this to here, it does not give me this. So they are diastereomers. So again, if I flip this, nitrogen's there, but hydroxyl group would have to be over here. So handy dandy table, we have isomers, or I guess a flow chart, I shouldn't say a table. Isomers, which are different compounds with the same molecular formula. Now we've talked about constitutional isomers, which are isomers that have different atoms bonded to different atoms bonded to different atoms. Then we have stereoisomers, isomers with differences in the 3D arrangement only. And then we have enantiomers, which they're mirror images, and diastereomers, which are not mirror images. So let's talk a little bit about some applications of this, and then we'll be done with the part of chemistry that we don't like. Now, research does suggest that the odor of many molecules is actually determined by its shape rather than the functional groups. So we have cyclooctane. This is what it looks like as a skeletal structure. This is its space-filling 3D structure. Then we have hexachloroethane. This is what its full structure looks like, and this is what its space-filled model looks like. Now, both of the above molecules have what we call a camphor-like odor, and you'll get to smell camphor later in the semester in one of our labs, because they both have roughly spherical shapes. Different chemical formula completely, but because they take very similar shapes, they have very similar smells. Now, why is that? Well, the reality is it all comes down to your receptors on your cells. They have similar shapes, thus they have the potential to interact with similar olfactory receptors on your nasal nose. I was going to say nasal something, but I lost what I was going to say. And so if they can interact with the same receptors, thus they can tickle the same nerves, thus appear to smell very similar to one another. And why is that? Again, it's all about that physical shape. Now, there's other examples of this too. So we have 2 different enantiomers can actually interact differently with smell receptors in the brain and have different perceived odors. So we have carvone A and carvone B. Now, carbone A is found in caraway seeds, and they smell like caraway. I don't really know how to describe caraway if you've never smelled caraway, but it has its caraway smell. I don't know. I can't think of how to smell caraway. But then you guys have probably smelled spearmint. Again, enantiomers to one another, same exact structure, similar 3D arrangement of molecules, but again, flopping over that 3D line. Now, why is that? Well, they have similar shapes. They're going to interact with the receptors in a similar fashion. And we see this idea all over the place. So for instance, the way that morphine works and many other, say, painkillers, well, they interact with your brain in the same way feel-good molecules like serotonin do, because they have very similar shapes. Similar shapes allow them to function similarly in your body. And I already talked about thalidomide, so I'm not going to talk about thalidomide again. So that's going to be the end for today. We're going to jump back in on Wednesday. We're going to go through some problems and how to draw enantiomers, and we're going to go through how we sort of interpret chirality centers a little bit more in depth. Yeah, so that's it.